Oh, perfect. All right. Okay, so first of all, thanks Dimitri and Sotiris for inviting me to give this talk. Okay, thank you for attending. All right, so I'm going to speak now about some recent work that, well, I initiated with Lucas and also working now, continuing now. And in principle, it has to do with non-Abelian integrable difference systems, discrete integrable systems. And specifically, it has to do with compatible maps. Either these maps are Yang-Baxter or other kinds of maps. Okay, so this is what I'm going to speak. And actually today I'm going to speak about hierarchies of maps and discrete integrable systems. And specifically, my talk is going to be based on these two papers, and of course, to results of other papers as we will see. Okay, so the outline of the talk will be the following. First, I will do a short, well, not so short introduction on what I consider to be a compatible map or Yang-Baxter map, and then, of course, I will say what is known in the literature about these maps. And then I try to introduce, let's say, the non-Abelian extension of these maps. That is the recent work with Lucas. And after that, I'm going to try to speak about extending these maps into hierarchies. Here, I have to state that actually we will have hierarchies of compatible maps. And this is because in a way, as soon as we have extended to the non-Abelian domain our original maps, in a way we have already hierarchies, or if you want, vector or matrix analogs of these maps. So I'm going to speak, if you want, of hierarchies of maps, but I will keep saying just hierarchies of map for briefly. And finally, I would just say a few things about how these maps lead to non-Abelian hierarchies of non-Abelian integrable difference systems, and to some known results. Okay, so let me start with the introduction, and let me start with what I'm going to speak about. Well, I'm going to speak about integrability, which is manifested by, let's say, compatibility of maps. In other words, common property that maps and integrable systems have. But give me one moment to move the bar here. Okay, now. All right. So let me start about that. Okay. So let me speak about integrability, which manifests by compatibility of maps. And let us start with X to be any set and the map from the Cartesian product of the set to itself. Okay. So also let us consider the maps Fij, where I and j belong to this set of natural numbers. And this map Fij will be the maps that act as the map F on the ith and the jth factor of this product. And it is convenient to denote this, in this case, three maps, Fij. So Fij is F12, F13, F23. Okay, it's an ordered set of maps in this way. And the map Fij would be called 3D compatible if the following, let's say, condition on composition of maps holds. Okay, this condition seems a bit, complicated. Actually, it is not. And actually, this is very closely related to what is nowadays called let's say, the consistency of integrable lattice equations, but I'll speak about that later. And okay, so I said this seems a bit complicated, but actually it is not. And maybe it's easier if one wants to understand this condition, if he wants to see it schematically in the following. Right? Yes, to see schematically the compatibility, if one thinks it on a cube. So actually, if one embeds the three maps, as I said earlier, F12, F23, F13 on the cube, and how we do that? I mean, we will just give the initial values, well, on U1, U2, U3 on three edges which share a common vertex on the cube. Then F12 is mapping U1, U2 to these two guys here from the bottom face of the cube. F23 maps F2, U3 to these guys here on the left face of the cube. And F13 maps the U1, U3 over here through the front face of the cube. Then, by using the right face of the cube and the map F23, we can calculate, first this red, the value of this red, the value of U3 to 1, but actually we can calculate this value in two different ways, from the left, from the right face of the cube, and from the bottom, from the back face of the cube. Similarly, this value can be calculated in two different ways, and this value in two different ways. And if we have the compatibility, so the values computed in different ways coincide, then we say that our map is 3D compatible. So to recapitulate, our map F is 3D compatible as soon as out of this map we construct the maps Fij, and we have a compatibility condition given here. As soon as the compatibility condition is satisfied, then we say that the map F is 3D compatible. Okay, alternatively, we can use the notion of Yang-Baxter maps. This notion of maps was introduced by Schiani and Drinfeld in 88 and 90, respectively. And actually, we will say that a map R will be called Yang-Baxter if it satisfies what is called Yang-Baxter relation given over here, where Rij again is the map that acts as R on the ith and jth factor of the threefold Cartesian product. Just to state it that solutions of this set theoretical solution of this Yang-Baxter equation was first introduced by Drinfeld, where actually he proposed the term to call these solutions as set theoretical solutions of the quantum Yang-Baxter equation. But later, Boostapper and Veselov proposed to use the term Yang-Baxter maps that is quite applicable nowadays, well, it's widely used nowadays. Okay, so this is what we can do. Actually, instead of compatibility of maps, we can use, let's say, as I said again, the notion of Yang-Baxter maps, as soon as, of course, as soon as one's, let's say, requirement has been satisfied. This requirement is the requirement of quadrirationality, and I'm going to speak about it later. And what I want to say here also is that something also well known is that instead of speaking of 3D compatibility or Yang-Baxter maps, we can speak about braid maps. And actually, if we have a Yang-Baxter map, one can have, let's say, well, a braid map, a map that satisfies this relation. Okay, this braid map is, or if you want to call it trefoil map, is related to the Artemis braid group B3. And okay, I mean, what is going on here is actually in the Abelian case, and when a condition has been satisfied, this condition of quadrirationality, somehow braid maps, Yang-Baxter maps, and 3D compatible maps are more or less the same. Actually, 3D compatible maps and Yang-Baxter maps are almost the same. But anyway, I will speak about that a bit later. Okay, so let us make here a small summary. I spoke about Yang-Baxter maps, I spoke about 3D compatible maps, and about let's say braid maps. But actually, if I want to distinguish map, it's better to use an equivalence relation. And the equivalency relations of maps is that two maps R and R hat will be called equivalent. Actually, if it exists a bijection K such that this condition holds. So R hat is equivalent to R if there is a bijection K such that this condition holds. at the same time, actually parallel to that, a map phi, a bisection phi will be called the symmetry of the map R if this condition now holds. This is, I'm going to use it a lot in the following. Also now I'm ready to speak about quadrirationality of maps. And I would say that the map R will be called quadrirational if the map R is birational, and if actually the so-called map, the so-called companion map of the map R that has been described here, actually shares with the map R the same graph. And or actually, if I want to say it better, if I have a birational map R, such that the companion map is also birational.
Pavlos, I'm sorry, I see a window which better to move away.
Ah, this window, okay.
Please.
So we see on our screen something called saying that please remove this window. Oh yeah,
oh.
Yep.
Yes, but one moment, maybe some windows on the background. Let me comment. Move this windows. Why is that? You can see it, huh? I don't know.
But never mind. I think we can survive.
I don't know what's going on.
Yes.
Okay, I try to move it wait. It seems that it disappears and reappears. I mean, if I don't do things. Okay, so let's see now. Okay, so this is what will be called quadrirational. So a birational map R from XY to UV such that its companion map is also birational will be called quadrirational. Actually, if you want, quadrirationality is somehow an extension or a generalization of invertibility of maps. But anyway, this will give a quadrirational map. And what is important here is that the companion map of a quadrirational Yang-Baxter map is a 3D compatible map, and vice versa. The companion map of a Yang-Baxter map is a 3D compatible map. I have to state that this is what has been somehow proven by other series, but these properties, actually the quadrirationality, yes, okay. This is given by other series. This is what I'm going to speak now about that. But what I'm going to say here is that actually maybe in the Abelian case you probably have a quadrirational map, but it doesn't mean that when you extend this map in the non-Abelian domain, the quadrirationality will be somehow preserved, as we will show later. And now what would be very important for my talk is that the lax matrices. And why lax matrices? Because actually I'm going to use lax matrices and I'm going to introduce maps out of the lax matrices of Yang-Baxter maps or 3D compatible maps. And okay, the definition of lax matrix, I will just maybe very quickly read the definition of the 3D compatible map, or the companion of the Yang-Baxter map, is that this map CR will be called, it has a lax matrix L that satisfies this condition here. Actually, to read it to say better is that a metric cell will be called lax matrix of the map CR if this relation implies this matrix refactorization problem, or and if and this matrix cell could be called strong lax matrix if the converse also occurs. In other words, if this matrix refactorization problem implies the map CR. Okay. The important thing is that from the same matrix refactorization.
Pavlos, can I ask something? So
yes, yes.
If this first condition generates a Yang-Baxter map, then always the second condition generates a companion, or is not always the case?
Yes, yes, it's okay. So if it is a Yang-Baxter map, yes, indeed. Indeed. But the opposite is not always true. I mean, as we'll see in the somehow in the non-Abelian setting, if you have a 3D compatible map, in order to have a Yang-Baxter map, you need an additional condition to be there. Yeah, this is indeed. But if you have a Yang-Baxter map, then you have also a 3D compatible map from the lax. Yeah, indeed. Okay, so this was given by the lax methods were given first by Suris and Veselov and also by Frank in 2002, I would say. And now let me give some examples from the literature and actually to state a nice geometric construction of Yang-Baxter maps and introduce, let's say, some equivalent classes of maps, of Yang-Baxter maps. And yes, okay, so this construction was given by Adler, Beko, and Suris in 2004. And it has to do with actually a pencil of conics. So actually, when we have two conics, we can intersect them with, they can be intersected in 5 different ways, as it is stated here. The generic case is when we have 4 simple intersection points, or when you have 2 simple intersection points at one point of tangency, or the other cases. I don't want to give the details, but actually, as soon as, for instance, let's take the generic case where we have, let's say, 2 conics and 4 points of intersections, we can intersect these conics with a straight line. And what other Beko series proved is that the map from xy, where x and y is, x is the intersection of the line with the first conic and y with the second conic. So the map from xy to uv is a Yang-Baxter map. Not only that, actually, they proved that this map is a quadrirational map. And for the moment, it believed that there was a classification of all quadrirational Yang-Baxter maps, but this was not the case, as I'm going to say a bit earlier. But actually, through this nice geometric construction, they provided us with, let's say, a list of equivalent classes of families of Yang-Baxter maps. They called it F-list. And this is explicitly how this list looks, reads. I don't know many things, but this is the list. And actually, a bit later, Papageorgiou, Tonkas, Veselov, and Suris realized that one can use the geometric symmetries of the pencil of conics, actually of the pair of conics in this case, and introduce more maps. And in this case, what they did actually, I don't want to pay much attention, is that if you have the Yang-Baxter map R and Phi be a symmetry, then one can formulate this other map R hat in this way, and then it's easy to show that this map is not Yang-Baxter equivalent or are not with the map R. R hat is not the Yang-Baxter equivalent with the map R. Okay, the equivalence is the equivalence relation with via bijection that I was speaking earlier in the definitions. And actually, up to this Yang-Baxter equivalency, Papageorgiou, Tonkas, Suris, and Veselov introduced 5 more equivalent classes of families of Yang-Baxter maps, which constitute the so-called H-list of quadrirational Yang-Baxter maps. So, I mean, in the Abelian case, well, it's not a complete picture, but the picture is the following, is that we have, let's say, 2 lists with 5 members each of equivalent classes of families of quadrirational Yang-Baxter maps. Okay, these maps are again were in the abelian case, and this is what was in the past. Of course, there are more works there, but I'm going to try to non-Abelianize these families of maps and extend them in hierarchies. Actually. Okay, so here is how the list of quadrirational Yang-Baxter maps reads. It was given again as by Georgiou, Tongas, Veselov, and Souris. And why everything I'm saying here is important is that actually the maps I'm speaking about, these Yang-Baxter maps, will be seen as different systems. And the important thing is that the compatibility property, either it is manifested by the 3D compatibility or by the Yang-Baxter property, this will be somehow a manifestation of integrability. And the maps itself, they can be seen as integrable edge systems. And under some conditions, from the empty systems, I can introduce vertex equations. What kind of vertex equations I can introduce? I can introduce some of the equations vertex equations that exist in the classification by Alterbo, Beko, and Souris. So actually, the Yang-Baxter maps of the F and the H lists are related, if you want, with the vertex equations that they lie below the red line of this list of integrable, this classifications list of integrable vertex equations. So this is the so-called ABS list of integrable vertex equations. Okay, so we have the Yang-Baxter maps of the F list and the H list will correspond to one of these integrable vertex equations if you want. Okay, so this is the case. And now an important question that I wanted to ask with Lucas is that, with Odoros, is that can somehow extend the F and the H list of maps of quadrirational Yang-Baxter maps to the non-Abelian domain. And actually, what is the non-Abelian version of F1 and the H1 Yang-Baxter map? Do they belong to the hierarchy? And the motivation of this thing is that if we do that, we will obtain hierarchical scalar maps in a way, and this will be a step towards quantization. I don't speak about quantization here because I don't have quantization because we don't have Heisenberg group. But anyway, we will have maps on non-Abelian maps. So actually, the symbols that they participate there, they don't commute. Okay, so that was our motivation, or maybe pure somehow curiosity. And so let me now state a bit at the non-Abelian setting what I want to do and how things would be settled. Okay, so I'm going to speak about maps which are somehow from the Cartesian product of x times x, where x is supposed to be the Cartesian product of A, let me call it A times, where A is a free associative algebra over a field F, for example, of the complex numbers with multiplicative identity. And AX denotes the subgroup of this associative algebra, which has multiplicative inverse. Well, in what follows with Z will denote the center of the algebra, which is of all elements which is a commutative subalgebra of AX. And well, examples of this set, actually, of this free associative algebra actually can be a division ring, for instance, quaternions.
Excuse me.
Yes.
May I ask a question?
Yes,
so,
yes.
A is a free associative algebra, right?
Yes, yes.
Then I think, if I'm not mistaken, any element does not have an inverse. You have a free associative algebra in it.
Yeah.
No
That's
way.
why I consider AX, where AX denotes a subgroup
But what are invertible elements in a free associative algebra? I think I do not see any invertible elements in a free associative algebra.
Yeah, but that's why I'm taking in my definition of the set X this A times, where A times is a subgroup of A.
But can you give an example of an invert of an element of AX, this group?
Okay. For example, okay, let's consider, for example, AX be quaternions.
But quaternions is not a free associative algebra. You say that A is a free associative algebra, right?
Okay, what about then if you take the subgroup of invertible matrices? For example, take, let's say, the upper triangular
okay,
matrices.
well, I think you mean that A is some associative algebra, not a free associative algebra. So you should remove the word free, I think.
Okay. Okay.
Because in the free associative algebra, there are no invertible elements at all. In the free associative algebra, there are no relations other than associativity, and because of this, there are no invertible elements at all in the associative algebra, only the unit.
All right, so let's speak about associative algebra then. Okay, okay. So yeah, no problem. Yeah. Yes. Okay. So actually, to be yes, okay. So not to be, let's say, too much formal. Okay, I will speak about, for example, maps on.
This can be corrected. Just remove the word free.
Okay.
Consider some associative algebra.
Okay, so it will be some associative algebra with a field. Okay, yeah, we'll do that. And all right, so then again, it's clear. I mean, I have this map R on. I will speak about this Cartesian property of the associative algebras, and actually, X could be a collection of variables, as it is stated here, and this could be my non-Abelian setting. And actually, I will speak now about our result with Theodoros. Is that actually we have this following family of maps, as I stated here, from x1, x2, v1, v2 to this u1, v2, y1, y2, where u1, u2, y1, y2 is given in terms of x1, x2, v1, v2 by these formulas. And provided actually the centrality assumption, what is the centrality adaptation? Centrality assumption tells me that, let's say that x2 times x1 is constant, it belongs on the center of the algebra, and y2, y1 belongs again on the center of the algebra. It's another element of the center of the algebra. So provided this assumption, what's going on for this map? This map has very nice properties. And what are the properties of this map? It has, let's say, two symmetries, two bisections phi and psi that satisfy the symmetry condition I gave in the introduction. This map has a strong Lax matrix, this matrix here. It is a 3D compatible quadrirational map, and the companion of the quadrirational maps is like that. And this companion map is a Yang-Baxter map. Why Yang-Baxter? Because it's a companion of the quadrirational map. What I have to state here is that actually the centrality assumption is needed in order to have the companion map, to have the map, in order for this map CK to be quadrirational. That's why we need the centrality assumption. If we don't have the centrality assumption, everything works up to 3D compatibility. So the Yang-Baxter map doesn't exist if we don't have the centrality assumption. The centrality assumption is important for the Yang-Baxter property. Okay, so this was our result. And what's going on actually here is that this K is a very general map. And what is going on here is that in the Abelian case, we just proved with Theodoros that this map K is equivalent with the H1 Yang-Baxter map. So in the Abelian case, what we have the H list and F list, and this is the case. But in the non-Abelian case, we have actually this gradation. We have two additional lists. We have the H list, the F list, and the K list and the L list. This is what we have proved. And This was in our work with Theodoros. And just to stay here, I just wanted to give explicitly the non-Abelian F list if you want. Here I put the red line in order to show what was known in the past in the literature. And actually, you can see now that F1, F2 is the new thing somehow. If you want, is the non-Abelian versions of F1 and F2 Yang-Baxter map. And you can notice here that, for instance, in the F2, that these terms 1 minus V, 1 minus V minus 1 in the abelian case will cancel out. And in the non-Abelians are very important for the Yang-Baxter property, but clearly not in the abelian because it will cancel out. And I think maybe that was the difficulty in the past for people to find, let's say, these non-Abelian versions of the F list of the F1 and F2 Yang-Baxter map, because it was not just the ordering that takes place in the non-Abelian extension, but also some extra expressions, extra terms have to be introduced in order to have the Yang-Baxter property. Similarly, also in the F1 Yang-Baxter map. All right, so that was somehow in the past, and now the thing is that can we do more? Can speak about hierarchies of 3D compatible maps or Yang-Baxter maps? Okay, I think.
Pavlos, I'm sorry. Could you return to the previous page? What is the class of algebras in which you consider non-commutative generalization, non-Abelian generalization? Is it just a free algebra?
Well, I'll speak. Well, for instance, division rings, for instance, quaternions, in order to be safe, if you want, not to face too much to speak too much about definition. So I will say I'm having an algebra with has multiplicative identity. And for each non-zero element of this algebra, each non-zero element of this algebra has an inverse. So I'll speak about the division ring, actually. Yeah, to be safe. But actually, I can have also the algebra of invertible matrices and work there.
For such in such generality, you claim the classification of Yang-Baxter maps.
Well, the thing is that classification up to this equivalency relation.
Equivalence, up to an equivalence.
Yeah, exactly. Up to this equivalence relation that I have here, classification doesn't exist, even for the abelian case. And actually, this is the natural equivalence relation if you want to classify Yang-Baxter maps, because this equivalency preserves the Yang-Baxter property. Earlier, I mean, in Integrable and Souris, they had an equivalence relation that preserves quadrirationality and not Yang-Baxter property. And actually, Integrable and Souris, they classified quadrirational maps and not Yang-Baxter maps. Mm-hmm. So even in the non-Abelian case, we don't have a classification, I have to state. And so that's why I cannot say that I have a classification of somehow non-Abelian Yang-Baxter maps, but I have large families of equivalent classes of Yang-Baxter maps in the non-Abelian domain, which include the abelian ones, of course, but also new things appear, new families appear as well. For example, these K and L lists, as I said, of Yang-Baxter maps. So indeed, I mean, somebody as I speak might think that I have a classification, but I would say that I don't have a classification for this reason, that even in the abelian case, we don't have a classification up to this equivalency, Yang-Baxter equivalency relation.
Mm-hmm. Okay, thank you.
Yeah, no, thanks.
Also, I think you use division ring, as you said, to be safe, but actually you don't need all your elements to be invariable, only a few of them. It's enough. And for the Yang-Baxter property and for the construction of the map, you only need a few elements to be invertible, not all of them. So in principle, you have even more general than a division ring.
Yes. That's correct. For example, the algebra of upper triangular matrices, well, with or defined on R with I don't know, with positive diagonal. I mean, for instance, and okay, this will work in case that my Yang-Baxter map is totally positive for you, totally positive, but yeah, I mean, you can have it. We can have it totally positive Yang-Baxter map. For instance, see the companion map of K. I mean, if I had C where C is parameters, but not Yang-Baxter parameters, just belong to the center of the algebra. For C negative, then this map is totally positive. So actually, we can have a map, a totally positive map. So clearly, I can say that X, Y, UV is just actually, well, UV in this case is just, well, let's say, for instance, upper triangular matrices with the entries real numbers, and well, on the diagonal, I have positive real numbers. Actually, everywhere I have positive real numbers. So this is really a good example, if you want, for this case.
Could you repeat? I didn't understand.
Yes. I have, for example, in this case, I mean, if we have C to be positive, I can have U, I, and VI to be upper triangular matrices, and with entries to be positive real numbers. Well, whatever I do, I will stay on this. Well, under the map, I will preserve this thing. I mean, always I will have yes, and of course, the positive real number. Yes, positive real numbers. Always, I will stay on this algebra. Whatever I do under the map, because it's a totally positive map. Totally positive map. Yeah.
Totally positive map. What do you mean?
I mean that well, for C equals is a negative real number, for instance, then I have only the numerator and the numerator. The map doesn't have the minus sign anywhere. If UI, VI are positive, the output of the map will be a positive real number, for instance. If I take it in the always.
Is it related with the totally positive matrices?
Yes, but yeah. For example, indeed, if you start with well, I don't know how to speak about total positivity in about cluster algebras, for instance. Here, I don't know yet how it would be. But the map is totally positive.
Okay.
Okay, so let me then continue, and then we speak about hierarchies of maps. And so I'll speak about hierarchies of map by introducing, let's say, this order n lax matrix, as it has been given here. Okay, this order n lax matrix, I would say that first appeared in the work of Frank and Papageorgiou and Capel in 1992, for instance, and well, and they were looking about not about in terms of Yang-Baxter maps or compatible maps, but they were looking in terms of integrable vertex equations. So this is the difference, and I wanted to say that in terms of maps, it was probably first discussed in Numi and Yamada in the Millian case back in 2002, where they actually gave this map D that I write it here. And I just want to state that this map D that's associated with this lax matrix in the non-Abelian case were given by Doliva in 2013, and earlier in the when we have the infinite metric scheme in by Nemo, I would say. Okay, so this is what is known on hierarchies of maps. That was, I think, the first thing known. And the other thing somehow known is that we can have a different arrangement of the variables on the map or on the matrix. For instance, this arrangement, this will give another map. Let's call it G. Okay, this map G is not Yang-Baxter equivalent in the sense that it is not equivalent up to equivalence relations I said at the introduction with the map D. Although the associated vertex systems will be equivalent. Anyway, so these are the things that they were known somehow in the introduction, this map G and the map D given here. And now I will say this recent contribution that, well, somehow I realized, I don't know, maybe it was known earlier, but the interesting thing here is that we can somehow deform these lax matrices by multiplying them from the left. The order where I'm multiplying is important because I have, well, we're in the non-Abelian domain. So I multiply both, well, I multiply them from the left, either, let's say, this lambda 0 or lambda 1 with diagonal matrices. The diagonal elements of these matrices are given here, where AI and BI are, let's say, belong on the center of the algebra. And clearly, and I obtain these new matrices lambda hat. Clearly, when, for example, AI is infinite, all AIs are infinite, I go back to the previous case that I stated that Doliva and actually Newman Yamada have. Or here, when BI equals 0, I'll go to the case 2 that I described earlier. Okay, so these are the diagonal deformations. For simplicity, what follows, I will consider AI and BI to be, let's say, 1. So actually, I would have this deformation matrix or perturbation matrix, if you like. And this is our new lax matrix that I'm considering the maps. So when we have this lax matrix L hat, given by the product of a diagonal matrix and the other matrix that I previously defined, we have this hierarchies of two hierarchies of maps, this K naught and K1. The K naught hierarchy looks like that, and the K1 hierarchy looks like that. So for each n, I have a, well, I have a map somehow, if you want. What I want to say here, okay, these are the two hierarchies of map. These are probably, new in the non-Abelian domain, defined in the non-Abelian domain. And what are the properties of these hierarchies? Is that they admit strong lax matrices that I stated earlier. They are birational. This can be proven in the paper that, on the archive version I have, are multidimensional compatible. And actually, one can introduce different families of multiplicative potentials that allows us to reintroduce, well, actually to reduce integrable vertex systems of equations, so lattice equations. So these are the properties of these systems. And what's important is that as soon as that, if we impose now the centrality assumptions, what we will get, we can also obtain Yang-Baxter maps. And actually, not only that, as I said here earlier, I mean, we post the centrality assumptions, we have quadrirationality, the companion hierarchies define hierarchies of Yang-Baxter maps, and we have the, actually, what are the lattice equations that we obtain, the vertex systems equations that we obtain as the lattice modified Gelfand equation and the hierarchy, and the lattice modified Nijhoff-Quispel-Capel Gelfand hierarchy, or Q3 hierarchy. This is actually what we obtain. This is maybe the main result. I mean, just I don't want maybe to put too much effort and to maybe tire you up. I mean, one can write implicitly the Yang-Baxter maps when the hierarchy, when the centrality assumptions are being imposed. And this is, let's say, the Yang-Baxter map. I mean, of course, this is implicit up to recurrence, but okay, if one wants, can do it explicitly after some work, but it's not so necessary. And now let me speak about this lattice-NQC Gelfand-Dicke hierarchy. For example, we start with hierarchy of maps K0. We can introduce potentials psi I via this relation of the map. And we have this rhombic version, if you want, of the NQC hierarchy. And in addition, if we add the centrality assumption, we can always eliminate to one field, and we obtain, let's say, if you want, the default symmetric version of the lattice-NQC Gelfand-Dicke hierarchy. Okay, why this is, I call it NQC hierarchy, is that because for n equals 2, we obtain the non-Abelian version of the NQC equation or the Q3 knot equation in other book when we released, that was given by Frank, Quispel-Capel. And for n bigger than 2, I have this somehow, if you want, the hierarchy of Q3 knot. And well, finally, before I finish, just to give, let's say, the similar things to speak similarly about the lattice potential KdV. I mean, I won't speak about the hierarchy here, just give the non-Abelian versions of the lattice potential KdV if you want. So actually, the non-Abelian version of the lattice potential KdV is here. Okay, it's been firstly derived by Frank and Chris Field. Well, back in the days, I think it was 2003 or 4, probably. And here I'm saying is that if you want, we can also have the rhombic lattice potential KdV that reads like that. And we obtain the default symmetric version or Frank's and the Field's version if we impose the centrality assumption again. Okay, so this is the thing that I wanted somehow to finalize this talk with. And well, about some small conclusions and what maybe will be nice to work in next is that about the elliptic case and actually the Q4 case. I mean, what about Yang-Baxter maps in this case? We have done some work and with Papageorgiou, Tassos, and Maciek Niesporski. But apparently, the thing is that, well, for me, it's not very satisfying because actually we have two-component maps that are related with Q4 equation. But actually, I would like a two-component map that is related to Q4 for some reasons. Okay, so this is what is next, and it would be nice to work with. And of course, I want to speak about the non-Abelian case. Also about Liouville integrability, it would be nice to look on Liouville integrability of the transfer maps in the non-Abelian domain. Okay, there we have some problems of what is the analog of the Poisson bracket, but okay, maybe in the far future will be some progress over there as well. But
well, you mean the analog of Liouville integrability, because the analog of Poisson bracket is it's the same actually, because it's like we have matrices. That doesn't change.
Okay.
But, and I think actually the Liouville integrability also doesn't change. It changes in the Grassmann case because you have half of the variables anti-commuting. But in the fully non-commutative case, I think everything is the same. Just think about matrices with commutative elements. It's the same.
Okay, I see. I don't know. I mean, I didn't know that, but maybe you're right, Sotiris. Well, for me, why I say that? So because I tried, for example, quaternions to extend things. It was not so trivial, not so easy. But okay, maybe you are right. Maybe you're right. One has to do it, to think about matrices and consider everything as matrices. Yeah. So this is what I wanted to speak about. And spasiba. Thank you very much.
Thank you.
Thank you very much. So you asked about the analog of the Poisson structure in the non-Abelian case.
The analog of?
What should it be? The analog of the Poisson structure in a non-Abelian case. I suppose it's a condition of the associativity, and the less interesting case is the free algebra. So it is interesting to impose non-trivial conditions to make an algebra associative and to produce maps which preserve these conditions. I suppose. Pavlos, could you come just few words about your choice of the equivalence condition for the solution for the Yang-Baxter map? Why this one? What does it mean in an algebraic point of view?
So sorry, wait, could you repeat the one? My choice of what?
Could you comment your choice of the equivalence condition for the solutions to the Yang-Baxter equation? Why choose this condition? There is a lot of different choices. My preferred one is a map in the Cartesian product, so not the diagonal one. It appears in some
this equivalence here.
Yes.
Okay, the thing is though that why is that? Because this equivalency really preserves the Yang-Baxter property. In the sense, for instance, if I take R12 hat to be, for example, phi1 times phi2, R12, phi1 minus 1, phi2 minus 1, then, well, you will see that with this case, I mean, this R hat is also Yang-Baxter. So really it preserves the Yang-Baxter property. If now you take, for instance, the equivalence relation, not to be, let's say, K times K, to be, let's say, K times L, where K and L are bijections, then this thing is not preserving any longer the Yang-Baxter property. The Yang-Baxter, let's say, compatibility, well, the Yang-Baxter equation. So that's why it's important, this thing. I mean, the classified quadrirational maps up to two, let's say, bijections, K and L. So they took the Cartesian product K times L. Then we have a problem in the sense that you can preserve quadrirationality, but not the Yang-Baxter property. If you just plug it into the Yang-Baxter equation, you will see that it's not satisfied by R hat. This is the reason. It's algebraic somehow. That's why this is the right equivalency. That well, it's not up to me. It's up to Papageorgiou, Veselov, Tongas, and Souris. That they showed actually that this is the correct equivalency. One should check one should try to classify Yang-Baxter maps.
You see, there is some approach to also to classify solution to classify the Yang-Baxter map. The map is just a map from x square to x square. You conjugate by such a map. There is a result of Solovyov, which makes all invertible Yang-Baxter map to the one leg form. So one leg is trivial, one leg is identity.
Yeah, I haven't seen this thing to prefer with you. I mean, I would be interested to see this equivalency. I mean, if you could send me, would really be.
It's a paper of Alexander Solovyov, and which is
okay.
I will send.
Yeah, I have to look at it because really for me up now, this is why I think this is the correct equivalency relation, the one should classify maps, because it preserves, let's say, the Yang-Baxter property. But maybe, okay, what you tell me now, maybe also, well, I cannot see it now. I cannot see how it preserves this thing.
Pavlos, and the last question about the hierarchy of maps. So could you just recall the relation between different elements of this hierarchy? Are they compatible between themselves, or?
That's why I speak about hierarchy of maps. I speak
Hierarchy of maps, yes.
because actually,
Is it just a parametric version, discrete parametric version of the Yang-Baxter map, or something else?
no, it has to do with the order of the lax matrix. For example, for when is the order of the matrix is 2. For instance, here I have the sorry, that is no, even here. Sorry, when the order of the matrix is 2, I have, for instance, the
What is the map? What is the map here? What is the
Yes.
map?
Sorry, what?
What is the map in this hierarchy?
The map is this one here, this D. And it has 2 n components, if you like, n in total x's and n in total y's. This is the 3D compatible map. If you want to go to the Yang-Baxter, you have to construct the companion map of this map that exists or when we impose the centrality assumption. But this is
it is a one map or a set of some family of maps?
Well, for each n, there is one map. Well, it's one map. It's a one map. Yeah, it's one map.
Okay.
Yeah. So, but for each n, well, you have a higher order maps. You have higher order spectral problems for itself. So in that respect, we have hierarchy. Here.
Okay. Okay. Thank you.
Yeah.
Hi, Pavlos. Can I ask?
Yes.
Connecting to this last question, actually, I had also. So you're not talking about commuting maps, are you? Or
no, I don't. No, I don't speak about commuting maps. I speak about maps that they do satisfy the Yang-Baxter property.
So when you're talking about a hierarchy, it is not a hierarchy of maps that have common solutions, for instance.
No. For instance, I mean, it's a matter of no. It's not exactly right, Frank. It's like, for example, we have the KDV and the Buzynski. So we have the map that corresponds to KDV is the other map, but also we have the map that the one that you gave with Tassos, I think, is the Buzynski map.
Okay.
Yes. So indeed, it's different. Yeah.
If there are no other questions, Pavlos, thank you very much.
Thanks a lot. Yeah.
Thank you all. We finish. Bye.
Thank you. Bye.